So good morning. Come to the webinar for the smart design, right? The first time with CETOL. So I will just give a brief introduction for what is CETOL first. As everyone may have already know what is the webinar for, we are actually going to do the tolerance analysis. So for CETOL Six Sigma is a variation analysis software for the assembly design. So I will explain later. And for the content of webinar today will be about what is symmetry, just a little bit of the history, and also who is using the CETOL, and how is this CETOL work, and when are we going to use it, and why we should use the CETOL, or maybe why we should use like during the design development or manufacturing course. So about the symmetry, it's actually having 30 years of history, and all is started in US. So in US, there is a company called Advanced Weapon System in Texas. And why they have started to develop this software is actually due to the concern that whether the assembly variation will actually cause some effect on the CAE simulation. Because at that time, they already start to do the CAE simulation and complying with the tolerance. And hence that's why they have actually collaborated with university and also for the CAP partner and go through along the time. PTC is our first Go partner to use the CETOL and so develop the software. And by later on, we also have the Dassault system to work with each other. So CETOL is actually able to work in SolidWorks and CATIA as well. And for the end of this history, come to today, we also work with Siemens. So for those who are using Siemens, actually can also use CETOL in their environment. And here will be the CETOL supported CAD system. So for integrated version, we'll be including SolidWorks and NX. And if you choose to standalone version, we also do have an option for NX and CATIA. And last but not least is for the PTC software who are using the PTC Cure CAD as their design tool. So in global world, who will actually using the CETOL Six Sigma? And here is the list. And we are actually have more than 1,000 customers. So if you see what is the field of the industry using it, actually it's quite a lot, especially for the medical, heavy equipment, transportation, and also the automotive. And for aerospace, also quite important for their complex system, where they actually need to study the assembly variation. And also for tolerance is very important. So what is CETOL? Just a little bit introduce about how we doing the tolerance stack up in traditional way. And I think everyone is familiar with the Excel sheet. So last time we only look at the drawing, and then we look at the closed loop to do a tolerance analysis. And this usually how we do it in traditional way to complete one cycle, and we are able to find out what is the worst case scenario for the plus and minus tolerance. So from here, I would like to compare how does this traditional tolerance to our CETOL. So for, let's say I give a scenario. Imagine that we are using a traditional tolerance analysis. So let's say I want to study the amount of gap between these two components. We usually will just view the picture in 2D and then measure the dimension in horizontal way. And also, if you focus to see these two areas, actually it can be rotated left and right, or even the other direction. But in traditional way, we only consider one direction. So by having this accumulation calculation, we actually only consider one direction, and we have ignore what happen if they rotate or it tilt to the other side, and so on. So I would like to introduce how CETOL handling this scenario. So in CETOL, we are allowed user how to illustrate this assembly happen, and also to take account for the tolerance. So for this kind of animation is taken out from the CETOL rather than the cat animation or something. And it's actually making it more realistic because for tolerance changes, it is considering for the wrapping between the pin and hole. And for the part positioning is actually uneven due to the gap. So this is the purpose why we need to do the tolerance to consider in 3D rather than in 1D direction. So let me drive further for the CETOL workflow. So as you see here, it's actually it's a 3D model here, and we're having with a few part component assembly on each other. How it determine is the contact surface. For the green area is the contact surface detected by CETOL. And later on, we will input the tolerance and dimension from the CAD, which is directly import, and we don't have to key in the dimension again. So, and even the geometric tolerance or GD&T, the datum, is actually can import from the CAD to the CETOL as well. So our expected variation will take a result is have a different type of the analysis, like normal distribution or lambda distribution also. So from this workflow, we can ask our own question whether it is assembled well, like whether they have interference or it is fully contact or not, or even it can be rotate or translate left and right or something. And we can also check if we have missed some dimension. So in CETOL, they have a feature where if it detects the missing dimension, it actually will give a reminder. So in management point of view, whether it is profitable. And then for how is it profitable or help the designer, I would like to emphasize for the tolerance contribution, where our usual 1D tolerance analysis cannot provide. So what we are seeing this bar here is actually for CETOL. When they have done for the analysis, they are able to tell you that which dimension is actually contribute or contribute more to the gap or dimension or the result. So if we want to improve our system or product, we just look for the first few scenario. It's either need to tighten our tolerance or actually you should change the dimension so that it can work well and reduce maybe less vibration or something. So by let's say if I choose one of the contribution here, once I done the analysis, if I change the tolerance from 0.4 to 0.2, actually the changes of the result will reflect instantly, and we don't have to run the software and solve again. So actually it can respond very fast. So one of the major advantage, as I say, it is really very fast. So what is picture you can see here is like total of 48 parts. For fourth state, actually is meaning that what kind of the assembly mode you would like to do or different scenario. And for measurement is meaning like, let's say I want to measure the gap here, the gap here, and how many measurement. So actually I would say it's less than 1 minute. And second is reliable. We are already have a standardized workflow to guide the user how to do the tolerance analysis. So we start from assemble to input dimension, and lastly to analyze the result. And the third one I would say is precise. It's a precise transient technology. So we are actually able to do a kinematic tolerance study in the 3D environment. And last but not least, is related to the DOF analysis. So even in the tolerance analysis, we are also having a term to call over constraint or under constraint. It's quite similar to the concept when we are doing the assembly in SolidWorks or in CATIA. If you are over constrained it is able to capture it and tell you that you should remove this constraint or this definition is wrong or something. And to explain why it can solve the analysis very fast, and this is the reason behind it. So the software is actually using the mathematical way to solve the sigma result. Like let's say they actually can calculate for the first moment, second moment, third moment, and fourth moment. And for the Monte Carlo method, actually is a random simulation method. So just example, if I threw a dice have a number from 1 to 6. So if I threw 6 times, maybe I cannot get 1, 2, 3, 4, 5, all this number. And I can only get 5 of 1 and 1 of 2. So because of this, the probability that is supposed to be 1/6, it cannot be reached. So it have to run a lot of simulation. But for CETOL, we are not a simulation tool. It actually is a mathematical solver. That's why it's a very fast solver. So for the feature that CETOL can do, like I say that it is quite similar to doing the assembly in the CAD. So we do have a 250 type of constraint for you to define how does this product look like. So if I have a little bit of time by the end of presentation, I actually will open up the CAD to show how is the interface of the CETOL as well. And we can even do the rotation here. So this is more on explaining what kind of different scenario we can do in CETOL. Like all these three pictures actually having a two same component. But for this first one, just a scenario that if I'm pushing this bike towards to the right, maybe it's too heavy. So that's why it is tilting up. It's contacting to the top of the bike here. And while the other end is touching the bottom of the bike here. And for the second scenario, is assuming that maybe the gravity is acting downward. So the piping will actually just landing inside here. While for the last one is more like maybe the other side have a component is connecting and making it to stay at the concentric position. So here will be at the center. And all these three scenarios will provide three different results as well. So actually we trying to do more realistic scenario to the product behavior. And to explain what it means for over constraint or not close. So you can see here, if all the member is closed, it will show the symbol to say it's closed. So what if when I do the assembly study, actually I'm lacking one more component and I couldn't complete the cycle. So it will also tell you it is not closed. And at that moment, you have to complete it so that you can run the study or tolerance you want. And this is another feature for the model graph. So don't be shocked about this model graph. Actually, it is automatically generated when we are doing the definition, and after we import all the dimension, it will help you to observe how is the relationship to different component or part. And this is the example of the CATIA environment. And we are able to import the MBD, model-based definition, into the CETOL. So the window here actually is showing that it's actually capturing the MBD, and we are able to change the value inside the CETOL. This is maybe a bit out of topic, but actually is a extra function of the CETO, actually together with the GD&T advisor. So but let's say if you are if your product design have a GD&T, then when you are doing the CETO, they will actually help to determine whether the definition you do, the annotation you add to the product is correct or not based on the GD&T standard. So if it's a bit is missing of the annotation or is wrong, it's also able to provide the recommendation or advise you to add or to remove. And one of the important that actually user want to see if we want to do the 3D tolerance analysis, sensitivity is the one that we are looking for, because we need to study for which part of the dimension or tolerance will affect the result that we want to achieve higher quality. So but let's say if moving one dimension, it will only affect the sigma by a little bit, then we are just ignoring that one. While if the sensitivity is very high, then we have to put our focus to study that tolerance, whether want to reduce or we can adjust for the dimension. And for the CETOL feature, for this one, we are also provide user to generate the report automatically, because it have already have a built-in report template. So for what you see here is actually exporting the result from the CETOL. So when are we usually need to use the CETOL? So it's during our design development, we have the conceptual design, detail design, and prototype building. And for the last one is the pilot and the mass production. It's more related to the manufacturing development. So I will just give an example. So how can the CETO act as the base to the manufacturing? But let's say I using the CETO, I analyze that actually for the side plate that we want to manufacture, they have total of top 5 contribution. And so we have to identify this one actually having a high contribution. We should take more careful about the quality. And then we need to choose which supplier giving a good quality or lower cost, or we just want to get balance between the quality and cost. So for the DPMU result, actually is calculated by CETO. So what is the input we need to get from supplier is actually the CP value. So once we can insert the CP value from the supplier into the CETOL to define the dimension control, then we are able to generate this result. For the DPMU is meaning that how many defect per million unit. So for supplier 1, they only have 11. For supplier B, there's almost like equivalent to 0, while supplier C is actually quite a lot. It's almost 3,000. But when we come to price, it is the cheapest. And for the highest quality, the scrap cost is almost 0, but for unit price is the most expensive. So we just do a little bit study for the cost comparison. Let's say for the company A, they only have a defect of 11 units. So when we come to the expenses and costs, it will cost 1,030,000. But for the scrap rate, it's only cost about $15. For the highest quality, we spend most of the cost, and the scrap rate is also equivalent to 0. While for company C, it's almost same expense to the company A, but we have the scrap rate of 4,000. So in order to get a good balance of the quality and cost, investors are able to see which supplier to choose. So for me, I will choose A because we are having a lower cost, but having quality and lower scrap rate. So why we want to use the CETOL? So I will try to highlight what is the key point. First is reduce the scrap rate because we are able to use the CETOL to calculate for the quality and also trying to reduce the cost. And secondly is to reduce the rework. So once we have the tolerance analysis tools, we no need to have more extra guesswork. And that's why it also eliminate the fit issue. And for it can prevent the torrent supplies and also avoid the manufacturing yield loss. So to summarize in 3 words, we are doing for reduce, remove, and avoid the risk. So for the second part to investment point of view, management point of view, it actually maximize the ROI and also make a better engineering decision. So it's bring the advantage of improving the quality. We have the faster product development. And last but not least is the cost efficient design. So it brings to a better, faster, and cheaper. And this is the overall of the CETOL that brings advantage to maximize the investment, to balance the product quality to manufacturing costs, and also faster time to market. And since then we have saved more time, we actually allowed to have more time to innovate a new product and have a better understanding to visualize the mechanical relation. So for CETOL, since it is actually have a standardized workflow, so it's still user friendly and also very easier to process for the knowledge. And for the technical support terms, actually for symmetry, they have a community that we are able to answer user question or they need support also able to respond very fast. Or I also can look for cybernetic system. Actually, me is a CETOL support as well. So thank you. And I think that actually I would like to show how is the interface looks like. So let me show the software. I think everyone can see that this is a SolidWorks interface. And actually for CETOL Six Sigma is in as an add-in. We are able to read the CAD from the SolidWorks and then import into the CETOL. So just a quick introduction, how are we going to do different scenario? This is a Arduino cover. So by right, I'm actually studying when the Arduino cover is closing, what kind of measurement I'm concerning about. So let's say with a tolerance affecting, when the cover is closing, I'm adding a requirement for the gap that it shouldn't be less than 0. So if less than 0, they're actually having the interference. So when doing the study, to get the result, so this is a visualization tool. For let's say I actually put the sigma for equivalent to 4, and we can start to animate how is the tolerance or dimension affect the gap between this cover and also the power adapter. I think CETOL is a very good tool there to help designer how to visualize it and what is the place or area we should avoid. For the result wise, because I set it very tight tolerance, so actually when I set it cannot achieve my requirement for sigma equivalent to 4 due to the too loose tolerance. And this is how is the contribution looks like. So it's showing me that for this hole is actually too small. It can pointing out which area I should focus and affecting the gap between this one, because this is the measurement that I set.